Hi everyone and welcome to this video about logarithms and how they're used to process nonlinear data. Before we begin the video, please remember to like and subscribe if you enjoy it. Feel free to comment down below any questions you might have about the video. And if you would like me to make a video on some content of your choice, place that down in the comment section below as well. So very often in real life, in science, we have relationships between data that aren't easily described by straight lines, or the lines such as y equals mx plus c. They're not easily described by quadratics or cubics or similar equations. They're described by exponential or nonlinear trends. So we're going to start off with the form y equals ax to the power of n. We might get data given to us that exists in this form, so what we can do is try and convert it into a form that is easily plotted on a graph. What we're going to do first then is to take logs of both sides. I'm just going to take log to the base 10 because then I can omit writing the base number. So on the right hand side of this equation, I've got this big chunk of algebra in the bracket. What I'm going to do then is use the laws of logs to break it down. First thing I can do is apply the multiplication law to split it up. Looking at this last term, I can see that using the power law will bring the n to the front. I'm just going to rearrange this here slightly. Remembering that x and y are the only unknown variables in this relationship, a and n are going to be constants. What I'm going to do then is just compare this to a regular y equals mx plus c equation. I'm going to take log y and compare that to y. Log x is going to be my x. And this in front, this n, is going to be the gradient m, and log of a is going to be my y-intercept c. So you can see that we've taken this nonlinear relationship y equals a times x to the power of n, and by applying logarithms, we have been able to write it in a form that is very similar to a straight line equation. In fact, now we can take this final line, this final expression, and try plotting it on a graph. So taking this now linear form of the equation and plotting it on a set of axes, we're actually not going to be plotting y against x. Through our comparison before, we saw that on the y-axis we actually wanted log y, and on the x-axis we wanted log x. We can see also that the gradient of this line is going to be n, and the y-intercept is going to be log of a. So we've taken this form and we've now been able to plot it as a straight line on our graph. Let's look at this second form of relationship we might get. Again, it's between y and x, but this time we've got a slightly different initial form with the two constants a and b. So again, I'm going to take logs of both sides. I could of course use ln, but I'm going to use log to the base 10. Using the multiplication rule this time, I can separate that out into log a plus log b, plus log b to the power of x. Then using the power rule, so we can see this again looks a little bit like a straight line equation. I have, in this case, log b as m, the gradient, again log a as plus c, x is just going to remain as my x variable, and for the y variable I'm now replacing it with log y. So on a graph, my y-axis is going to be log y, my x-axis remains the variable x, the gradient in this case is log b, and that y-intercept there is going to be log a. Let's take a look at this example question together. We have a graph of log n against t. So first of all, we need to find a way of transforming our equation n equals a times b to the power of t into an equation that includes log n and the constant t. So we take n equals ab to the power of t, apply log on both sides. We're then going to use the laws of logs on the right, and finally bring the t down to the front of that log. So I've written it like this so we can see that log n corresponds to our y value, t would correspond to our x value, log b would be the gradient, and log a would be the y-intercept. Using that information, I can now compare log a to 1.6, which is the y-intercept, and then raise that 1.6 to be the power of 10, and calculating that, I find it to be 39.81. So it says two significant figures, let's round that then to 40. We now need the gradient to be able to compare that with log to the base 10 of b. That would be my calculation there. Now I can take 10, place that at the base. That fraction works out to be 0.095, so I raise 10 to that power. If I work that out, that is 1.2 to two significant figures. So now we have to interpret the meaning. So we're going to have to go back and understand what all of these variables mean. N is the number of people who have fallen sick, T is the number of days. So when T is 0, we know that we're going to be at the y-intercept. So A in this case is going to represent the initial number of people who have fallen sick. We can now replace A and B in our original equation. N equals 40 times 1.2 to the power of t. After 30 days, we know that t will be 30, so 40 multiplied by 1.2 to the power of 30 is 277. The question then asks, give one reason why this might be an overestimate. A sensible answer might be that there is natural immunity, the virus might spread slower, people might be staying at home after they realize that they've taken up the virus and so slowing the rate of spread. Just a sensible answer like that will answer the question. Let's take a look at this second example. In this case, we're asked to find the value of k and t. This is a very simple question, but it's here just to show that we can have other forms of exponential equations for modeling, not just the ones that I've shown you before. In this case, we are given a pair of numbers, t equals 100 when m equals 42. All we have to do is substitute those into our equation, and now we're going to solve this by dividing both sides by 60, taking the natural log of both sides, and dividing both sides by 100. Let's convert that into a decimal, so k is minus 3.567 times 10 to the minus 3. Now for part b, I'm going to replace k and replace m. So 30 equals 60 e to the power of minus 3.567 times 10 to the minus 3t. So I have a half equals e to this power. I can take the natural log of both sides, divide both sides by that negative number to find t. And that is 194. Let's interpret the meaning of our answers. So K is in fact the rate at which this radioactive substance is decaying. M is the mass at the moment. 60 is the mass at the start. T tells us how many years after the initial observation we are at. So in part B, for the mass to drop down to 30, in fact, the time taken is going to be 194 years. Thank you for watching this video. I'm glad you've made it all the way to the end. If you have any questions about the video, remember you can leave them down in the comments section below. Please like and subscribe if you enjoyed it, and I will see you in the next video.